Okay, so series day 2, we started with this warm-up. So when a ball is dropped, you don't count the first drop twice because it literally just fell from a height of 10. But then after that, the motion comes in pairs. So it goes up 0.36 times 10 and back down 0.36 times 10. The third bounce would be 36% of that, so you could write that as 0.36 squared times 10 and back down 0.36 squared times 10. So if you want to add up all the motion, it's 10 plus, and then you have 2 0.36 times 10s, and you have 2 0.36 squared times 10s, like that, and so on. So you could pull out a 20 actually here. And this is infinite behavior. Of course, in the reality, the ball will stop bouncing, but theoretically, according to this description, the ball bounces forever like this, you see? Okay, so you can kind of see a G-series being built here, and the G-series is just this part in brackets. And the first term is 0.36, and the R is 0.36, which is unusual. You don't usually have the same A1 and R, okay? But it did happen on this problem. So anyway, you have a 20 on the outside, and then that series will go to A1 over 1 minus R. And if you type this into your calculator, you get 21.25. 21.25 what? Feet. What does it mean?
That's the total distance.
This is the distance the ball travels. You'd actually have to wait for eternity for it to actually happen. So it's all very hypothetical, and it's all kind of very silly, really. The ball can't actually do this, right? The ball will stop bouncing when it stops bouncing. But in a theoretical model, it would take forever to travel this distance. But if you waited forever, it would not travel an infinite distance. It would travel 21.25 feet. Interesting. How many of you have done this problem before? It's quite a famous problem.
I've done similar problems.
Similar problem, yeah. So the first thing we did today is we saw how G-series can model real behavior in the real world. Okay? So, all right, let's just review what we did last time. So we kind of have, I want to do a review every day of what we've talked about, because like I told you before, this chapter can get pretty challenging. So last time we saw that there's an algorithm to finding convergence value of infinite series, and it entails 2 steps. First, writing an explicit rule for Sn, and then finding the limit of Sn as n goes to infinity. I have no idea why I left such a big blank for n goes to infinity.
Because it's infinitely long.
Yeah, okay, yes. I felt bad writing infinity small, so I think I'm going to write it really big.
Do it.
Okay? So the idea is to try to understand how the adding is working, and then try to understand its end behavior. It's quite challenging. If you look back in the day 1 notes, you'll see getting Sn took us forever. On example 3, for example, we had to do a telescoping series. And a telescoping series, the easiest way to see the Sn is to sort of write out all the Sn expansion explicitly, and you'll see the terms that remain. And Sn sort of finally popped out at us. There were 4 surviving terms out of an infinite number of terms. Only 4 survived. Okay? Example 2 also was hard. Example 1 was hard. But we were able to construct those Sns a little bit easier. Okay, we also saw that some infinite series have a sum. What do we call that?
They have a sum.
When they have a sum. Finite. But we say the series, what? Converges. So some of them will converge and others will diverge, which means there is no sum. So these 2 words just literally mean, in the case of series, have a sum and don't have a sum. Okay? Now, last year, your teacher gave you a series like this, 3 halves plus 9 fourths plus 27 eighths, and asked you, what does this all add up to? And you wrote no sum. And the reason was R is 3 halves. And when R is bigger than uno, we actually don't have a sum. Even if r is equal to 1, we don't have a sum. So you might remember writing no sum last year, but this year we write diverge. Okay? But it means the same thing. Let's go to this next line. We learned that if the terms of a sequence are not diminishing to 0, then the series automatically diverges. So on your worksheet, we're going to pause right now and just go over the first few problems on your worksheet to make sure you guys wrote divergent for the right reasons. Okay? Let me pause the recording. Okay, so this brings us to what's called the harmonic series question. Okay? This series is very famous right here. This is called the harmonic series. And it just basically goes 1 plus a half, plus a third, plus a fourth, plus a fifth, etc. And for some reason, this guy is misbehaved enough to where this does not add up properly to give you a whole number, or a number. Like this thing will not converge. So why will it not converge? It seems like all the terms are so small. 1 plus 0.5 plus 0.33, etc. Why is that not going to give us a value? Okay? So this guy is called the harmonic series, and even though its terms are getting tiny, for some reason it adds up to infinity. Why is that? How can we show that this thing diverges? So who was the first person that realized it diverged, you know? How did they know it diverged? Maybe Mr. Harmony, possible. Okay. Okay, so here's a very easy way for us to see that the harmonic series, 1 plus a half plus a third, etc., actually has no sum. I think you'll be able to follow this very easily. Okay, so I tried to type this up for you. First thing you'll notice is that I've given you a graph, and on the graph you have the red dots, which represent the series 1 over n. Okay? And then you have the black curve, which represents the curve 1 over x. So I do have a typo here. This should say f of x here. The curve represents f of x equals 1 over x. So what I'd like you to do is, starting at 1, we never start at 0 with the series. Starting at 1, draw a rectangle with area 1. Okay? So after you draw it, go ahead and write 1 in here. Now go over to x equal, or n equals 2, and draw another rectangle. This one's going to have area half. See if you can make the second rectangle have area half. Try to make the third rectangle have area 1/3, and so forth. Okay, so draw in those rectangles. So you're sketching 10 rectangles with areas equivalent to the terms, 1, half, a third, which means you might want to think of 1 plus a half plus a third plus a fourth plus a fifth as 1 times 1, 1 half times 1, and so on. So think of this as base times height, base times height, base times height, and so on. So your rectangles literally are all right here. Just a bunch of LRAM rectangles that start at n equals 1. So there's a total of 10 of them. The last one extends, from 10 to 11 there. And you can put the areas in here. This is literally area half. This is literally area 1/3, 1/4, 1/5, 1/6, and so on, all the way down to 1/10. Now, if you get out your calculator and you add 1 plus a half plus a third, blah, 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 all the way up to 1/10, you will get the following decimal on the calculator screen. 2.9290. That's if you add up the first 10 rectangles. Okay, now, under the curve, the black curve, there is also an area. Right? Now, we would not get this by doing rectangles. We would do this area in black using integration. Right? Okay, so let's use our calculator also to run the integral from 1 to 10 of 1 over x. So I'll give you a second to do that. I'll pause the recording. Okay, so that black area is just found by doing integral 1 to 10, 1 over x. You could just do this by hand. I mean, it's just ln x from 1 to 10. So it's just ln 10 minus ln 1. But your ln 1 is 0 there. So what did the calculator spit out for this calculation? 2.3025. Yeah, I actually rounded it to the nearest 10,000th there. So you'll notice something about the black and the blue. Which has the greater area, the integral or the series? The series, right. So do you think that trend is going to continue? Do you think that these LRAM rectangles are going to be larger area than the curve forever? Should be. We know that on any decreasing curve, LRAM rectangles actually give a value too large for their area estimation, right? Okay, so we can make a small conclusion about how this would behave as we keep going. So let's clear this out and scroll down a little and write our conclusion. How do you think we could generalize? Oh, what do you notice? We noticed that the integral from 1 to 10 of 1 over x dx is actually less than the series n equals 1 to 10, 1 over n. How do you think we could generalize this as the number of term goes to infinity? I think we could say that the integral will always yield an area less than the series would. I think that's safe to say. Now we would like to find this integral right here. Okay, now your calculator, unless you have a T99, you probably cannot get your calculator to obey you on this and actually do this integral because it's improper, right? But you could do this by hand. So I'm going to do the integral from 1 to infinity of 1 over x dx. This is an improper integral, so you'd write limit as b goes to infinity, 1 to b, which in turn is limit as b goes to infinity, ln absolute value x from 1 to b. And here it is, limit as b goes to infinity, ln b minus ln 1. ln 1 is just 0, of course. Okay, time to make b large. What do you get when you take lim b goes to infinity of natural log b? B to the million, or sorry, ln of a million, ln of a billion, ln of a trillion, what is that going to give you?
Infinitely.
It'll go infinity. And so what we see here is that the integral diverges. The integral diverges, right? Since this improper integral diverges, and the series is larger than it, if you look back one step in our work, up here it's saying that the series is larger than the integral, it too diverges. Or it diverges also, you see, right? The series diverges also. So if the black area under the rectangles is infinite, and yet the blue area is larger than that, then we have a divergent series, you see. So I'm just going to go back to my picture that I had earlier and draw a little bit here for you to just sort of grasp it a little bit better. Did everybody write this down so I can erase it? Okay, so watch. We'll just scroll up a little bit so you can see. We were saying basically that these rectangles have larger area than the black area under the curve, right? But then after that, we proved that this black area is actually infinite. Black is infinite. What does that tell us about the blue? Blue area is infinite, right? It's larger. That's the logic. It's very sound logic. Something that's bigger than infinity is clearly infinite. Okay, so this is a great way for us to understand a series. We can think of it as an integral problem. Okay? let's say that you're trying to do a complicated series and you just don't think you can handle it. You could turn it into an integral problem, solve it, and then you can understand a series by doing an integral. So let's go to the next part where we actually do some examples of this. Oh, by the way, it turns out that if the black area under here is finite, like, 1/3 or 0.16 or whatever, then the rectangles will also be finite. That's a little bit harder for me to prove, so we'll skip that today. It's just a little harder to convince people of that, but I think it's in your book. Okay, so let's go down here now, and let's state this little two-pronged theorem. The theorem says this: if f is positive and continuous and decreasing, and you're trying to study a series that has the same expression f, then you can study the integral. And if the integral converges, then so does the series, and if the integral diverges, then so does the series. This theorem here is a little bit wordy, but it's just basically saying, take a series problem, turn it into an integral, do the integral. If the integral converges, then so does the series. If the integral diverges, then so does the series. Okay? Now, we have to have positive functions to use this rule, which means you can't have anything that's going like under the x-axis.
No signs.
Yeah, you can't use like sine waves and stuff. So your functions have to look like this. They have to be decreasing, they have to be positive, they have to be continuous. Okay? But if your graph looks something like this, just going down like that, and you suspect there might be an area to study here, an interesting area, you can test to see if that area exists using an integral. Whatever the integral tells us, that's what the series is going to do. All right? All right, so I kind of typed it twice. You'll see this at the top of the next page too. Okay? All right, let's try this out. Now, use the integral test to show that this series converges. This is a tough series. I imagine you could spend a whole week collecting terms and trying to create an S sub n formula. It's not worth our time. What if we just wanted to know if it converged? Well, let's see what the integral looks like. So you would just write this integral 1 to infinity e to the x over e to the 2x plus 1. You turn it into an integral problem. You would then try to solve this integral. You guys are pretty good at integrating, most of you. You might recognize that if you let u equal e to the x, du is e to the x dx. Right? Which means you could actually rewrite this integral like this. Boy, that looks familiar. Arctan u, right. That's correct. Where u is what? E to the x. So I'm going back to blue, which is back to x now. Okay, now there's a little more to this. You're supposed to do from 1 to b, and then let b get big. It's an improper integral. But I'm going to abbreviate my work just a little bit by erasing the integration work, okay? So this is something you could have done on the side of your paper. But basically, this comes out to inverse tan of e to the x. Now, I'm supposed to go from 1 to infinity. Obviously, I'm not supposed to do that. It's improper. So I'll just put a b up top. And then we'll put a lim b goes to infinity here. Okay? So you end up with this. lim b goes to infinity tan inverse e to the b minus tan inverse 1 e to the 1. Sorry, e to the 1. Thank you for alerting me. And it's a little bit hard to think about, but if you let b go to infinity, then e to the b is going to go to infinity. But arctan of infinity is actually pi over 2. If you think about the, look, let me show you. This is the arctan graph. This is one of the graphs you might want to know. This is the graph of arctan. So if e to the b is growing really big, this graph is climbing towards pi over 2. So this is actually pi over 2 minus, and then the limit b goes to infinity cannot affect that second term at all, because there's no b in it. So this is our answer, pi over 2 minus inverse tan of e. And if you must know, this is 0.35251. But notice that it's a number. That's all I care about. This is a number. What does that tell us?
It converges.
The series must converge also. The rule of the day is this. If the integral converges to a value, then the series does too. Okay, I tried to show you that with the rectangles, try to convince you of that. So we can say that this series converges. Now, I don't dare say it's 0.35, but I know it converges to something. And I know it's actually a little bit near this, probably. You know, with point something, maybe. If that makes sense. So we're just going to go ahead and state our conclusion in black up here. Since the integral e to the x dx over e to the 2x plus 1 converges, so does the series e to the n over e to the 2n plus 1. And if somebody asks you, oh man, you got to justify that, you just say, integral test. And they'll say, okay, fair enough. You did the integral, show me your work. And then you show them your work, and you say, I got a value here. And they say, okay, then the series converges, and you're quoted the right rule, quoting to justify. Okay? Now, do you think on my test I would say, show that this converges, or just ask you if it converges? I would ask you to show if it converges or diverges. So I would leave that ambiguous. This next one, again, on this next one, I'm telling you it diverges. I won't do that on the exam, okay? But for our first time, how would we show that this diverges? Well, we could simply use an integral. So we will do this integral. Turn the series question into an integral question. And in fact, I'm going to start doing this. I'm going to start making my sentence have math in it. So I actually already wrote the first word of my sentence. I put, since the limit as b goes to infinity, 1 to b of 1 plus, integral from 1 to b of 1 plus x to the minus half dx is equal to the limit as b goes to infinity of 2 times 1 plus x to the positive half between 1 and b, which in turn is the limit as b goes to infinity 2 root 1 plus b minus 2 root 2 equals infinity. Since this work is giving me infinity, the improper integral diverges. Therefore, the series diverges. The series diverges by the integral test. So I'm turning my limit problem, my series problem into a integral problem. Whatever the integral does, that tells me what the series does. Okay? Pretty cool. So you can see how you had to know improper integrals to do this chapter. It's impossible to get past the first step on that sentence without it. I think you should write sentences with math work in them. I think that's a good habit. This is how math textbooks are written, right? The work is just thrown right into the middle of your sentence. And you should learn to type it too. So you should get Microsoft Word and start typing equations. The editor is very, very user-friendly now. It's not like it used to be if you ever tried to type equations in the past. It's improved so much with Windows 7 or Microsoft Office, whatever it is, 10 or whatever. Okay, you already did this problem last night on the worksheet. But you could compare this to the integral 1 to infinity 1 over x to the 1.1. And if you run this on your calculator, you're going to get the integral comes out to 10. Now, that means that the series must converge. I won't say it converges to 10, but I will say that the series converges. The next one is tested by doing integral of 1 over x dx, which really comes out to infinity. You can show your work later. So I would conclude that the series diverges. In your last case, you would run this integral. You can do it on your calculator or play around with it by hand. This too diverges. So we turn these into integral problems, we check for convergence, and then we conclude. I also wrote some concluding remarks at the end here. Okay, so I'm just going to go over real quick. You guys can pack up. I just basically wrote that today we used the G-series to understand a motion problem. So this should be 1, 2, 3, 4 bullets. So we used G-series to understand motion. We talked about whether something will converge or not. And this last problem you're going to want to memorize. Memorize that last example and the results thereof. So the bell rang, but I just want to review these here. So we just basically talked about how you can use a G-series to understand a motion problem. That's the bouncing ball problem. We studied that if a function is decreasing, positive, and continuous, so basically like this, and it looks like there's a sequence with dots on it, and you have a sequence or a series that gives you dots right on this curve, then basically if there's area under the curve, then the red segments add up to something finite, and if the area under the curve is infinite, then the red segments add up to infinity. It's a good way to understand bullet 2 there. So we're using the integral to test the series. Next is bullet 3. Any series of this format here, where it's 1 over a changing value to a constant power, is called a p-series. And we'll talk more about p-series later. But basically, p-series will always converge if p is greater than 1, and diverge if p is less than or equal to 1. This is off your worksheet last night, too. If your p is exactly 1, it's divergent, and it's called the harmonic series, so it has a name. And now we actually know 3 types of series that will converge. The telescoping, the G-series when r is less than 1 will converge to a value we can actually find, and a p-series when p is less than or equal to 1. That should say p-series when p is greater than or equal to 1. Let me fix that little typo there. Let me fix this. This is a pretty big typo, actually. There we go. Okay, so that's been fixed. Those are convergent, but we wouldn't claim to know what they converge to. We just say they're convergent. And then the harmonic case, that's a known divergent. It's actually good to know what series diverge. So I think you should memorize this last fact, that the harmonic series diverges. So the next time you see this guy, n equals c to the infinity of 1 over n, you should know immediately that this is divergent. And the reason is because its antiderivative is basically ln, which grows, albeit slowly.